Today we are going to start with the concept of induced EMF. Basically, we studied about the concept of EMF, right? And
Yes.
now the things which we are going to talk in the new section that is related to electromagnetic effects, right? So this topic is actually from electromagnetic effects. And in this, we are going to talk about the combined concepts of electricity, magnetism, and their combination.
So it's like the chapter 18, the new one.
Yes, basically this is the new chapter because in practical electricity, we discuss about some concepts of power, energy. Then we discuss about the three-pin plug, the uses of the safety precaution, the safety hazards we discuss. And previously we
Yes.
discussed about the static electricity and the magnetic properties. So now we have to start the concept that is linked with the combination of electricity plus magnetism. So the first concept is related to the induced EMF, right? Basically,
Yes.
in induced EMF, we are going to discuss about the EMF definitely, but that is the induced one. So we have to study that what is the concept of the word induced over here, right? Because we normally discuss the concept of that EMF will produced in the circuit, but induced is the new term. So basically, let's suppose if you consider a magnet, and if we are having a magnet, there will be a north pole of a magnet.
This is the same as electromagnetic induction, right?
Yes. And this is the south pole. And you already know about the magnetic field. So what will be the direction of magnetic field
From north to south.
from north to south? So magnetic field will move from north to south. And let's suppose if we are having a wire or a conductor over it. So this is the wire, and we are going to move this wire in downward direction. That is completely perpendicular to the magnetic field, right? Let's suppose if
Yes,
you
yes.
drop something from the table, so basically that object moves perpendicular to the surface of the table, right? Because surface of the table is
This wire will be on north or south pole, like where?
basically this is like a 3D concept. Like if you take the example, like there are two chairs placed at some distance, right? So the first chair is the
Yeah.
north pole and the second one is the south pole, just like the position in the diagram, and there is a gap. Okay.
Okay.
And if you drop the ball between those two chairs, right? So ball is
Yeah.
actually moving in downward direction, right?
Oh.
So magnetic field is on x-axis and ball is moving in downward direction, that is on y-axis, right? So that is the concept. So basically you placed a wire in perpendicular condition with the surface of the chairs. So wire is actually going to move perpendicular to the magnetic field. Okay.
Oh.
So that is the concept because we have to study about another quantity. So that's why we are going to mark the 3D diagrams. So to take the third quantity in the diagram also. So basically, there is a concept that if we move conductor or wire through the magnetic field, right? So there will be an
Okay.
EMF, or there will be, we in simple words we can say that current will produce in the circuit, right? Let's suppose if you take the example of the windmill, right? So actually what windmill do, that when wind starts to flow through the windmill, right? So the turbine of the or the motor of the windmill starts to rotate, and when it
Yes.
starts to rotate, so it will generate electricity, right? So we are generating electricity with the help of that mechanical energy taken by the air molecules. So we are going to do the same thing with induced EMF. that we are going to move that wire perpendicular to the magnetic field or through the magnetic field. So that will give you the
Okay.
quantity of electric current, right? But that
Yes.
value is very much short, because when you just move a conductor through the magnetic field, so there is a limited area or region where magnetic field is actually flowing. So very small amount or very little amount, like in microamperes, electric current will induce, right? So basically we are going to write the statement like this: when a conductor or a wire when a wire is moved through the
Oh, like what is the meaning of induced?
yes, I'm going to explain that one. Let's
Okay.
suppose if we consider the situation when a wire is moved through the field lines, the field line is for the magnetic field, right? Because we are
Yes.
already having a diagram, so we are talking about magnetic field. So when we are moving through it, so basically the wire actually cuts the magnetic field line. And when the wire cuts the field line, so the free electrons in the conductor or the charges in the conductor are starts to move, right?
Yes.
Starts to move. And when a charge will starts to move, so the moving charges are known as electric current, right?
And yes.
So that concept is known as the induced EMF. Why we are using the word induced EMF? Because there is no direct connection, right? Because in normal electricity chapter we discuss that we connect wire with the battery, and then charge will starts to move through the wire, okay? But this time we
Yes.
are not using any source. There is no source connected in whole diagram, in whole circuit, but still there is a quantity of electric current, right?
Yes.
So we can say that this concept is known as, so this induces an EMF in the wire, okay?
Okay.
So basically in simple words, or in other words, we can say that we are working with the induce concept. And further, if you want to explain the concept of the word induce, so you may explain this concept like this: that when EMF will be induced in a conductor if there is,
So like this induces an EMF basically means like there's current.
yes, so basically that is current, a very small amount of current, right?
Yes.
But if we are using a simple concept like current will produce, so that will confuse you sometimes when you are working with different concepts. So you are not able to understand that either it is produced with the help of magnetism or from the battery, right?
Yes.
So that is the concept. So if there is relative movement between the conductor and magnetic field, right? So when we are talking about the
Yes.
movement of the conductor and the magnetic field or their relative motion, so then we are going to get the concept of induced EMF, right? Otherwise not. When we are working with the direct sources like battery cell or the power supplies, so that will give you the concept of normal electric current, right? And second thing
Yes.
is also possible. In this situation, we are moving wire through or conductor through the magnetic field. But let's suppose if we consider a second situation. So in second situation, we can consider the situation like this, that if we are taking a magnet, let's suppose there is a north pole and a south pole, and this is our magnet, and we are going to move this magnet through a coil, right? Now you
Yes.
can see that there is no electric source connected with it, right? There is
Yes.
no
Yes.
battery. Now there is not another source connected in the diagram. There is only two things: coil and a magnet.
Magnet.
Further, yes, further we will connect a measuring instrument which is known as ammeter to note the value of electric current, right? So
Yes.
this is the concept. So basically, in the first diagram, we discussed that conductor can be moved through the magnetic field that will generate EMF, that is known as induced EMF. And the second possibility is that you can also move the magnet through the wire. So that will give you the same concept of induced EMF. So both possibilities are there, right?
When it passes through that wire, there will
Yes.
be current.
Yes. Again, you will get the same concept of induced EMF. So we can say that,
These two are same thing.
yes. So when the magnet enters the coil, the field lines cut through the turns in the wire, inducing an EMF, right?
Yes.
So you can see there are two situations, and in both situations, you are getting an induced EMF. So both possibilities are there, right? So normally, actually, what is going on there that will induces an EMF, right? So when you move the conductor through the magnetic field, or when you are moving the magnet through the wire or through the conductor, so actually what happens that your field lines will actually change, right? Because when magnet starts to move through the coil, so you can see that if we just mark the magnetic field lines, so that will be crossing the conductor like this, right? And when you starts to move that magnet through the coil, so your field line actually changes, right? And due to that field
Yes.
line change, or due to the change in the field lines through the conductor or through the magnet, EMF will induce over there, right?
Yes.
So basically, if we talk about the reason that why this actually happens in your situation, So the reason is that when a conductor or a magnet moves through the field
Like the wire, yeah.
coil, yes,
And the wire, yes, when passes.
yes. So basically, if we are working with the conductor, so we used to write with the reference of field, and if we are working with the magnet, so we have to move through the coil, right? So this is the difference only. So when a conductor or a magnet moves through the field or the coil, the magnetic field lines change or changes. So the magnetic field line changes, and due to that change,
Yes,
due to change in field lines, an EMF will induce. So this is the concept. Okay.
oh,
So because we know the thing that what we are actually talking about, what we are actually doing in this process, but the thing is that uh, why and how this things actually works, right?
yes,
So the reason is that due to the change in the magnetic field, this actually happens, right?
yes, yes,
So due to the change of the magnetic field lines through the conductor or in the magnetic field, this EMF, induction of EMF actually take place. So this is the important thing that we discuss, right?
yes.
And there is an other thing that what will be the
If
direct.
we
Hmm?
change like the position of the magnet, will if like
Yes.
we change it?
Yes, so that is the question. That if we place magnet from the south pole over here, so what actually happens, right? Because in south pole, magnetic field lines are opposite. Okay,
Yes,
so
up,
that is the thing. And if we move magnet close to the coil, if we move magnet away from the coil, so there are two possibilities also, that if we change the pole and if we change the direction, so what will happen, right? So that is the question. So if we discuss about that, because initially we got the concept, yes, EMF will induce and how it will induce, we are okay with that. But now what happened when we change the direction, right? So there are two
yes.
possibilities: either we are moving magnet close to the coil, or the second possibilities is when magnet is pushed away from the coil. So there are two important things. So the first one is, if we consider the first situation, and in first situation we consider that when magnet is moved close to the coil,
With the north pole facing or the south pole?
north pole facing, because from the north pole field lines are coming out, so that's why we use the concept of the north pole, right?
Yes.
So when magnet is moving towards the coil, this is the first thing that we are going to discuss. And in this concept, let's suppose if we consider the north pole, and north pole is actually moving towards the coil, right? And let's suppose if we
Yes.
connect this coil with the ammeter that shows you the value of the electric current, right? So I'm going to draw the direction of the arrow that will indicate you that in which direction your EMF will induce, right? Either in forward direction or
Yes.
in backward direction, right? So basically, when your magnet with the north pole is moving towards to the coil, so your deflection of the coil or your direction of the current will be in forward direction, right?
Again.
Right. So basically, when your magnet is moving towards to the coil, so EMF will also induce in the forward direction. Okay.
Okay.
So this is the first example. And you know that when your magnet is moving close to the coil, so the pole that we are going to get over here is known as the south pole, because your magnet is moving towards the coil, and you know that when the magnet passes through the coil, so definitely there will also be a magnetic field, right? Because when current passes through the coil, so EMF will sorry, magnetic field will also generate. Okay. So when
Yes.
conductor
Okay.
passes through, sorry, current passes through the conductor, so magnetic field will generate around the coil. Okay. So when
Okay.
magnet is actually passing through the coil, so EMF will generate over there, and due to that induced EMF, definitely your coil will get north pole and south pole because of magnetic field, right? So this point
Okay.
will become south. Okay.
Okay.
Sorry, this will be your north actually, because north pole is close to this point, so this will become the north pole. And the problem is that how to remember this thing. So to remember this concept, there is a law which is known as the Lenz law. So there is a concept of Lenz's law, and Lenz's law
Okay.
explains you the direction of the pole, that how the magnetic field will generate in the coil when magnet is moving towards the coil or away from the coil, right? So according to the statement of the Lenz law, we can say that the direction of an induced EMF, so the direction of an induced EMF always opposes the change that produce it. So basically, by the statement of Lenz's law, you can identify that the direction of an induced EMF always opposes the change that produces it. So if you try to understand that this concept with the help of the magnetic field, so when north pole is moving towards the coil, right? So the
Yes.
point on the coil nearest to the magnet will be the north pole. Now you can identify that north pole will repel each other, right? So basically it opposes the change which actually produces it, because the north pole is responsible for the induced EMF in the coil, right? And
Yes.
the magnetic field in the coil actually opposes the north pole, right? So that's why north pole produces over here, and the direction of the north pole will be in opposite direction. So now you can see both are acting in opposite direction, right? And this direction can be identified with the help of the Lenz's law, right?
Yes. Yes.
EMF induced in the forward direction, but the magnetic field that is, or the magnetic pole that is produced near the coil is completely opposite to the pole which is coming towards the coil or towards the conductor. And if you consider the
Oh,
second case, so in second case, when magnet is moving away from the coil, so when a magnet is moving away from the coil, so your north pole is actually moving away now. So your north pole is moving in this direction, and we are moving away from the coil.
the direction will also be the opposite.
Yes. So in this, your EMF will induce in the opposite direction. So the direction of an EMF will be at this point. And if we talk
But what
about,
is the arrow for?
basically this arrow shows you the deflection in the meter, right? Just like the speedometer, when your speed increases, so it will move in forward
Okay.
direction, and when your speed decreases, so that will show you the decreasing direction. But in ammeter,
Okay.
we are using ammeter over here, because ammeter shows you
The
the
value.
value of electric current. So these deflection will show you the direction. It is not showing that your current is decreasing. It actually shows you the magnitude with direction. Okay. So in second part,
Oh,
we are getting opposite direction only. Still, we are having a value of an induced EMF. And if we talk about the closest point, so the closest point on the coil gives you south pole this time, because a south pole actually attracts the north pole. But the problem is that north is moving away and south is trying to attract that north pole. So again, you are getting opposite direction. Okay.
okay.
So this is the concept. So in the first case, in the first diagram, you observe that there is a case of repulsion, right?
Yes.
So in case number one, the end of the coil close to the magnet, close to the magnet will become a north pole, and the second we are getting in case number one is
Yes.
it means that It will repel the north pole of the magnet. So this is the point related to the first point or the first case. And if we consider the second case, so in the second case, the end of the coil which is close to the magnet will become a south pole, right? And second thing is
Yeah.
it means
It will repel the south.
actually it is going to attract the north pole, but the problem is
Oh
that
yes, yes,
north pole is moving away, right?
yes, yes. Then it will repel also.
Yes.
How will it attract it? Like moving away.
Basically the north pole is moving away, right? Because when we are just moving or pushing the magnet back from the coil, right? So
Mm.
that will generate in the induced EMF, but the pole that is actually generated on the closest point of the coil, that will be south. So south actually wants to attract the north pole, but the problem is that we are moving north pole away from the coil, right? But if we
Yes,
talk about the force, so force will be force of attraction, right?
yes,
And we know that due to change in the magnetic field, EMF will induce, and the EMF will induced over there. And according to the Lenz's law, we identified the direction in both cases when the pole are moving close to each other or close to the coil, and when poles are moving away from the coil. Okay.